In the beginning, there was nothing. Then, suddenly, the universe as we know it was born from a singularity, an event we now call the Big Bang. These events have been meticulously studied, and one such theory that further elucidates on this is the inflationary universe hypothesis. Introduced by American physicist Alan Guth in 1981, this hypothesis claims a rapid expansion period during the cosmic era, thus resolving some of the issues presented by the Big Bang theory. Picture a point infinitely dense and hot, exploding and expanding at an unimaginable rate. This was the ignition of all that we know today. Within the first fraction of a second, the fundamental forces of nature were forged: gravity, electromagnetism, and nuclear forces, all setting the foundation for the universe to come. As the universe cooled, particles manifested, then atoms giving birth to the first elements, hydrogen and helium. Fast forward a few billion years, these elements congregated to form stars, galaxies, and eventually planets like our own. The 1990s introduced us to the phenomena of dark energy and dark matter. These concepts, dark matter initially proposed by Jan Oort in 1932, and dark energy later, helped resolve issues such as the missing mass of the universe, Einstein's static universe paradox, and why the universe continues to accelerate. Now, as we continue our journey through the cosmos, let's ponder on the potential endings of our universe. Theories suggest a myriad of possibilities. The Big Freeze, where the universe continues to expand, cooling and losing energy, until it can no longer sustain life. The Big Crunch of the Big Bang, where gravity pulls everything back into a singularity. The Big Change, a phase transition that alters the very laws of physics. Or the Big Rip, where dark energy tears apart all matter. Each potential scenario holds a captivating allure, reminding us that our cosmic story is vibrant and ever-changing. Today, due to advancements in technology like telescopes, satellites, and computer simulations, we have been able to explore deeper into our cosmos. The development of space telescopes like COBE, Hubble, Wilkinson Microwave Anisotropy Probe, WMAP, and Planck has been invaluable in our exploration of the universe and in precise measurements of various parameters in the Big Bang model. From a single point, the universe has expanded into the vast cosmos we see today. Every atom in your body was once part of this cosmic event. The Big Bang is not just a theory, it's our origin story. We are all stardust, connected to the cosmos in the most fundamental way. Regardless of the uncertain final chapter of our universe, our shared cosmic narrative remains intertwined with the Big Bang, marking the inception of the universe as we know it. Recent estimates place the age of the universe at about 13.8 billion span of cosmic history we are intricately woven into. End of voiceover. Having journeyed back to the Big Bang, we now delve deeper into the mystery that surrounds this cosmic event. Many believe the Big Bang represents the start of everything. But is it really that simple? The Big Bang theory, supported by over 50 years of scientific evidence, tells us that the universe was born from a massive explosion, giving birth to matter, space, and time. But this theory leaves some questions unanswered. It tells us that the universe was once concentrated at a single point, a singularity, but it doesn't explain what this singularity was or what came before it. The singularity, a point of infinite density and extreme heat, is believed to have existed for a brief moment, known as the Planck epoch, before the forces that govern our universe separated and took their current forms. This moment was so dense and energetic that all four fundamental forces, gravity, electromagnetism, and strong and weak nuclear forces, are thought to have been unified. But how did this unified force function? And how did it give birth to the universe as we know it? These are questions our current theories still struggle to answer. From this singularity, the universe expanded and cooled, transitioning from a state of uniformity to one of increasing complexity. Quarks and gluons combined to form protons and neutrons, which eventually formed atoms. It took 180 million years for the first stars to form, and 400 million years for the first galaxy. Over billions of years, this process continued, resulting in the cosmos we observe today, filled with diverse galaxies, stars, and planets, including our own. But remember, the Big Bang theory doesn't claim to explain the origin of the universe. Rather, it describes the evolution of the universe from a particular starting point. What came before the Big Bang and what caused it is still a mystery waiting to be unraveled. The Big Bang is more than just the beginning. It's a critical chapter in our cosmic story, but it's not the whole story. As we continue to explore the universe, we may discover more about our origins and the mysteries that the Big Bang theory has yet to unravel. End of voiceover. As we delve deeper into the mysteries of the cosmos, we must address the evidence that supports the Big Bang Theory, our best explanation for the birth and evolution of the universe. This theory, which posits that our universe emerged from an infinitely hot, dense state that was nearly uniform, is supported by four key pieces of evidence. First is Hubble's law, named after American astronomer Edwin Hubble. Using the largest and most powerful telescope of his time, Hubble measured changes in the brightness of various stars over time. His calculations helped us determine the distances to galaxies where these stars were present. According to Hubble's law, the farther a celestial object is from us, the faster it recedes, as evidenced by the increasing wavelength of light from distant objects. Second, we have the cosmic microwave background, or CMB. This is a uniform radiation found in all directions and everywhere, just a few degrees above absolute zero. It's the afterglow of the Big Bang, offering us a snapshot of the universe at a very early age. Third, we have the abundance of light elements such as hydrogen, deuterium, helium-3, helium-4, and lithium-7. These elements existed in space before the formation of any stars, and their presence supports the Big Bang Theory. And finally, the fourth piece of evidence is the large-scale cosmic web. This vast cosmic structure, which becomes denser and more clustered over time, with larger spaces between its masses growing, is a testament to the expansion of the universe. These four elements, Hubble's law, the presence and characteristics of the CMB, the abundance of light elements, and the expansion of a large-scale cosmic structure, form the foundation of the Big Bang Theory. Yet the Big Bang Theory can take us even further back in time, to a time when energy goes beyond the limits of tested physical laws. This is where the mysteries of dark matter, the imbalance between matter and antimatter, and the very origins of our universe lie. As our understanding of the universe expands, so too does our curiosity. What secrets does the cosmos still hold? As we continue our journey, we may just find out. End of voiceover. Before we move forward, let's take a step back and look at the universe from a different angle. The Big Bang Theory, a foundational pillar of cosmological thought, has captivated the minds of scientists and laymen alike since its inception. It is a theory that has fundamentally shaped the way we perceive our universe. However, despite its widespread acceptance, the Big Bang Theory is not without its share of theoretical conundrums and challenging paradoxes. For instance, when we try to rewind the cosmic clock, tracing our steps back in time to a hypothetical moment when our universe was in a state of incomprehensible heat and density, logic seems to falter. In such intense, overwhelming conditions, the very laws of physics as we understand them lose their footing. Quantum fluctuations, the incredibly tiny changes in energy that occur in a quantum system, could under these conditions create black holes of enormous magnitude. These black holes could potentially engulf the entire universe as we know it, leading to scenarios that defy our understanding of the natural world and making it difficult to comprehend the reality of our existence. However, as we strive to understand the origins of our universe, a gleam of enlightenment has emerged in the form of the cosmic inflation theory. This theory, which was first proposed by the remarkable physicist Alan Guth some 4 decades ago, paints a slightly different picture. It suggests that before the universe reached the hot, dense state that we associate with the Big Bang, it underwent a period of rapid expansion. This rapid expansion, or inflation, serves to resolve some of the paradoxes that were inherent in the Big Bang Theory, and provides a feasible mechanism to explain some of the observed characteristics of our universe. During this period of cosmic inflation, the universe would have been devoid of matter and radiation. Instead, it was filled with an immense volume of energy, a form of energy so profound that it constituted the intrinsic curvature of space. This energy is what drove the universe to expand at an exponential rate, culminating in the creation of a flat, empty, and uniform cosmos, with the only exception being those quantum fluctuations. This period of inflation eventually came to an end, transforming the energy of space into matter and radiation. This transformation gave birth to the Big Bang explosion, which in turn led to the emergence of our observable universe. While there is still much that remains unknown and unexplored about cosmic inflation, the data that has been collected over the past 3 decades provides compelling evidence in favor of its existence. This theory not only challenges but also reframes our understanding of the Big Bang, suggesting that it was not the origin of everything, but rather the start of the universe as we know it. End of voiceover. Building upon the cosmic inflation theory, we delve into an even more mind-boggling concept, the multiverse. According to this concept, our universe, with its 14 billion light-years of cosmic history and hundreds of billions of galaxies, is but a minuscule speck within a much larger cosmos. This cosmos, or the multiverse, encompasses a vast, possibly infinite number of universes, each with their unique properties and laws. The idea of the multiverse is a direct consequence of the inflationary theory. If our universe underwent a period of rapid expansion, then it is likely that countless other regions of space did the same. These regions, separated by vast expanses of inflating space, could each form a separate universe within the multiverse. Each of these universes may have different physical laws, different types of matter, and perhaps even different dimensions of space and time. The concept of the multiverse is truly staggering, and it brings forth new questions about our place in the grand scheme of things. Are there other forms of life out there in these other universes? Could there be other versions of ourselves, living out different lives in different universes? And most importantly, will we ever be able to prove the existence of these other universes? The multiverse theory is still in its infancy, and we are just beginning to scratch the surface of this profound concept. However, the mere possibility of its existence has already started to reshape our understanding of the cosmos. The Big Bang, while still a crucial part of our cosmic history, may no longer be the definitive beginning. Instead, it might just be the start of one universe among a potentially infinite number of universes, each with their own unique histories and futures. As we continue to explore the cosmos and unravel its mysteries, who knows what other incredible discoveries await us? Perhaps one day, we might even find definitive proof of the existence of the multiverse. But until then, we can only marvel at the sheer scale and complexity of the cosmos and continue our relentless pursuit of knowledge. End of voiceover.